For example 2, we're going to be sketching some graphs. So it says sketch the graph of the following rational functions and then state its domain and range. When you are looking at rational functions, the first thing you want to think about are where the asymptotes have moved, if they have moved. Because the asymptotes sort of create a barrier for your graph. So it's important to state where your horizontal asymptote and your vertical asymptote may be before you move on from there. So starting with the horizontal asymptote, and then we'll look at the vertical asymptote, and then we'll work with it from there. Okay, in terms of the horizontal asymptote, normally the horizontal asymptote is at y equals 0, and you'll notice that shifting the graph up or down will actually change the location of your horizontal asymptote. Because this graph has been shifted down 1 unit, what that tells me is that the horizontal asymptote has moved from y equals 0 to y equals -1. Okay, so based on the horizontal shift that I have here. Okay, the vertical asymptote is normally at x equals 0. Because the graph has been shifted to the left 5 units, what that tells me is that the vertical asymptote is going to move with it. And so now where the vertical asymptote will be is at x equals -5. So it's moved from 0 to -5. Okay, so those are two things that we wanted to start with. So what I'm going to do is I'm actually going to graph the asymptotes first. So I have an asymptote at y equals -1. So I'm going to draw that first. And remember that asymptotes are drawn using dashed lines to indicate that it's not actually part of the graph, but it's sort of like a barrier in the graph where the graph cannot touch. And then at x equal to -5 as well. So here I have y equals -1. And here I have x equals -5. Don't forget to label your asymptotes. Okay, so that sort of forms a barrier for my graph. So I know my graph is either going to be based on the asymptotes either in the first and third quadrants or in the second and fourth quadrants. Okay, so now what I'm going to do is I'm going to use my key points and I'm going to apply my transformations to get my new set of points, draw those points, and then sketch a curve that gets closer and closer to the asymptote. So my key points for a rational function are -1, and -1, and then 1 and 1. Okay, in terms of our mapping formulas, the graph has been shifted to the left 5 units, so I know my x values are going to decrease by 5, and the graph has been shifted down 1 unit, so I know my y values are going to decrease by 1. So from here, and in case you're wondering where I got these numbers from, remember all your horizontal transformations are going to be in the denominator, and all your vertical ones are going to be the numbers on the outside. And so I'm going to take each of these x values and decrease them by 5. So -1 minus 5 is -6. 1 minus 5 is -4. -1 minus -1, so if I look at the y values now, is -2. And 1 minus 1 is 0. Remember that this is a rational function, so you should expect your graph to either be in these two quadrants based on where your asymptotes are, or in these two quadrants based on where your asymptotes are. Okay, so if I plot these points, I have a point at -6 and -2, which is here. And I have a point at -4 and 0. And you'll notice that right now my graph is in the first and third quadrants based on my asymptotes. And so if I sketch a curve, all I need to do is sketch a curve that gets closer and closer to the asymptotes. And then that's pretty much it for graphing rational functions. So they're actually one of the easier graphs to create, since you are just sketching a graph that gets closer to the asymptotes. And that's it. Okay, in terms of the domain and range, the domain and range depends on where the asymptotes are. So I'm going to start by writing x as an element of all real numbers such that the only restriction on the value of x is that x cannot be equal to -5 because we have an asymptote there. So x is an element of all real numbers such that x cannot equal -5. And similarly for the y values, y can be all numbers except wherever the horizontal asymptote is. And in this case, the horizontal asymptote is at -1. So y is an element of all real numbers such that y cannot equal -1. Okay, so there's one example of graphing a rational function. So you want to think about where your asymptotes are first, draw your asymptotes, then look at your key points and your transformed points, sketch those 2 points, and then sketch a curve that gets close to the asymptotes, and then from there you can state the domain and range easily. As long as you really know where the asymptotes are, you should be able to state the domain and range anyway. Okay, here's another example of graphing. So in this case, we have a little bit more transformations. And so if you look at the denominator part, it's already in factored form. There's no coefficient in front of the x for us to worry about. So let's start by looking at where our horizontal asymptote and where our vertical asymptote have moved. Okay, horizontal asymptote is normally at 0. Shifting the graph up or down moves it. So I'll notice that the graph has actually shifted up 3 units. So I'm moving from y equals 0 to y equals 3 in terms of my horizontal asymptote. In terms of the vertical asymptote, normally the vertical asymptote is at 0. The graph has been shifted to the right 1 unit, so that means my vertical asymptote has moved to x equals 1. Okay, and again, I'm going to draw those first. So I have y equals 3. And I have x equals 1. Okay, and again, now I'm going to start with my key points, apply my mapping formulas, get my new points, and then go from there. So x and y, and then I'm going to have my new set of points as well. Okay, in terms of my x values and y values for my original points are at -1 and -1, and then 1 and 1 as well. And so if I look at my horizontal transformations, the only transformations I have in the denominator is that the graph is shifting to the right one. So the x values are going to increase by 1. In terms of my vertical transformations, notice that you have a -2 at the top, which tells me the graph is going to be reflected in the x-axis and then stretched by a factor of 2. And then it's going to move up 3 units as well, based on the +3 that's at the end. So I'm going to apply these formulas to my x and my y values. So -1 + 1 is 0. 1 + 1 is 2. -2 times -1 is 2. + 3 is 5. -2 times 1 is -2. + 3 is 1. So if I plot these points, I have a point at 0 and 5. And I have a point at 2 and 1, which is here. And what you'll notice in this case is that instead of my graph being in the first and third quadrants, based on where your asymptotes are, this time the graph is in the second and fourth quadrants based on where the asymptotes are. Now, why would that have happened? Well, notice that the graph has been reflected along the x-axis. So what happened is the part of the graph that would normally be up here has moved down here, and the part of the graph that would normally be down here has actually moved up to the second quadrant. Okay? So now that I have my 2 points, all I'm going to do is sketch a curve that gets close to the asymptote. Try not to touch the asymptote and try to extend your graph as far as the grid goes as you're drawing it as well. Okay? And I just realized I forgot to label my function. So this is h of x. I forgot to do it in the last question. So I'm going to go back and fix that really quickly. So I should have actually labeled the graph here g of x. All done. Full communication works. Okay, and I've labeled this one h of x. Now your last step is just to state the domain and range. So in terms of the domain, the only value of x that I can't have is wherever the vertical asymptote is, so x cannot equal 1. And in terms of the range, the only value of y that I cannot have is where the horizontal asymptote is, so y cannot equal 3. Okay, for our last example, this one's going to be a little bit different. And so in this case, again, we're sketching the graph, and then again, we're going to state the domain and range. But you'll notice that in the denominator, we have more transformations. What you'll also notice in the denominator is that it's not actually written in factored form. So my first step is to rewrite this in factored form. So this would look like -1/3. If I factor that out, I'm left with x minus 3. And you can check really quickly. -1/3 times x is -1/3 x. -1/3 times -3 would give me +1. Alright, now that I have my transformations, because be careful, the reason why you need to make sure you have this in factored form is, in the original problem, it looks like it's a horizontal shift to the left 1, but if you actually looked at it in factored form, it's actually a horizontal shift to the right 3. So that's why it's important to make sure that your function is in factored form. So, in terms of my horizontal asymptote and my vertical asymptote, So let's take a look at what's going to happen here. Horizontally, again, normally it's at 0. Shifting the graph up or down is what's going to move it. Because the graph has been shifted up 2 units, I know the horizontal asymptote has moved up to 2. Vertical asymptote is normally at 0. Notice that the graph has been shifted to the right 3 units, so that means the vertical asymptote has moved to x equals 3. So now that we have our horizontal asymptote and our vertical asymptote, we can look at our key points. So -1, -1, 1, and 1, and then we can look at our transformed points as well. Okay, in terms of our horizontal transformations, there's been a reflection along the y-axis, a horizontal stretch by a factor of 3, and then a horizontal shift to the right 3 as well. Okay, so reflection in the y-axis, stretch by a factor of 3, shift to the right 3. In terms of our vertical transformations, notice that there's only a 1 at the top, so that's not actually being stretched or compressed, but it is shifting up 2 units, so I'll get y plus 2. And then again, substitute in your numbers and evaluate from there. Before I do that, I should actually draw my asymptotes, just so that I have a barrier for my graph. So I have my horizontal asymptote at y equals 2. And then my vertical asymptote at x equals 3. And then I can find my points. So -3 times -3 is, -3 times -1 is 3, plus 3 is 6. -3 times 1 is -3, plus 3 is 0. -1 plus 2 is 1, 1 plus 2 is 3. So now I have a point at 6 and 1. And I have a point at 0 and 3. And again, you'll notice in this case that my points are no longer in the first and third quadrants based on the asymptotes, but instead are in the second and fourth quadrants based on where the asymptotes are. And the reason for that is because, again, there was a reflection in the graph. Except this time it was a horizontal reflection. So the part of the graph that was up here in the first quadrant has been reflected to the second quadrant. And the part of the graph that would normally be in the third quadrant was reflected onto the fourth quadrant. Okay? And so again, I'm going to sketch a curve that approaches my asymptotes. And what you'll actually notice in this case is that, notice that this point here is 3 units away from the asymptote, and this point here is again 3 units away from the vertical asymptote. Because the graph has been horizontally stretched by a factor of 3, that means that the graph is now 3 units farther away from the asymptote than it normally would have been. Normally it was only 1 unit away, now it's 3 units away. Okay, just a quick way for you to check. So I know this function is f of x, and now we can state the domain and range very easily. So x can be all real numbers except where our asymptote is, so x cannot equal 3. And then similar idea for the range, y can be all real numbers except where the horizontal asymptote is, and in this case it's at 2.